We've all heard the buzz, right? Microservices, distributed systems. Kind of feels like the gold standard for modern tech these days.
Yeah, absolutely. It's been the prevailing wisdom for years now.
If you want to build something cutting edge, scalable, resilient, well, the story goes you break it down. Tiny, independent pieces.
Exactly. And monolithic architecture often gets pushed aside, seen as this cumbersome, outdated legacy thing.
That big ball of mud phrase comes up a lot, something you'd rather just not touch.
Right. But what if I told you that today, in 2025, the monolith isn't just like still relevant, it's actually making a surprising comeback?
A comeback, really?
Yeah, and for some very compelling, often overlooked reasons. We've done a deep dive here, looked at, gosh, over 70 diverse sources, industry reports, case studies, technical papers.
70 sources, wow.
Yeah, it's pretty comprehensive.
Mhm.
And the crucial finding, monolithic architecture offers significant, often really measurable advantages in specific contexts.
Okay, so not everywhere, but in the right place.
Exactly. We're talking real, tangible benefits, performance, cost, team productivity, things that many organizations are now, well, rediscovering or even actively choosing to go back to.
Migrating back. Now, that's a massive twist to the usual narrative. I mean, who would have thought?
It is a twist.
So today, we're diving deep into this world of monolithic architecture. We're going to unpack what it really means, get past that simple big ball of mud label,
Yeah, move beyond the stereotype.
and explore these surprising performance and cost benefits you mentioned. We'll even look at some major companies making these big architectural moves that really challenge what we've been hearing for years.
Some big names, definitely.
Our mission today really is to arm you, our listener, with the evidence-based knowledge, help you make informed architectural decisions that truly fit your specific needs.
Right. Moving beyond the hype.
Exactly. Beyond the industry hype to the practical stuff, what genuinely aligns with your team, your capabilities, your business goals. Let's unpack this surprising resurgence.
That's it, precisely. It's about practical fit, not just, blindly following the latest trend. And to really get why the monolith is having this renaissance, we first need to understand what it actually is.
Okay.
And maybe more importantly, what it isn't in its modern form.
So let's start right at the very beginning. When we say monolithic, what are we truly talking about? It sounds, well, singular, almost unyielding.
And that's exactly right. The word itself gives it away. It comes from the Greek roots, monos, meaning single, and lithos, meaning stone.
Ah, single stone. Okay.
Yeah, so picture a single indivisible block, solid, unified. In software terms, this means all the essential parts of an application.
Like the UI, the business rules.
Everything. The business logic, the data access layers connecting to the information, the user interfaces you interact with, all the supporting functions underneath. They're all built, deployed, and executed as one cohesive unit.
One unit.
Fundamentally, it's one code base that leads to one deployment package, and it runs as a single process.
So it's like a single, tightly knit ecosystem where everything lives together, talks directly to each other.
Yeah.
But for those of us, building this stuff day to day, what does that really look like practically?
Yeah, good question. In practice, this unified nature translates into several core characteristics that really define a monolith and, crucially, underpin its strengths. First off, there's the single deployment unit.
Okay.
This means the entire application, the whole thing, is packaged and deployed as one single executable or service. When you update something, you push one complete package. The whole application updates in one go.
Right. So no coordinating 50 different service updates.
Exactly. It dramatically simplifies the release process, just fewer moving parts to manage.
That immediately sounds less complicated than juggling dozens of microservices.
That certainly can be, yeah. Secondly, there's usually a shared database. Typically, all the components inside the monolith access one common centralized data storage system.
One big database for everything.
Pretty much. And this is a massive simplification for data consistency. All parts of the app are inherently working with the same unified view of the data. You sidestep the complexities and potential inconsistencies you get with distributed databases or, eventual consistency models often found in microservices.
Which I imagine has huge implications for things like financial transactions. Or maybe inventory management.
Oh, absolutely.
No distributed transaction nightmares, which can feel like, I don't know, trying to conduct an orchestra with everyone in different soundproof rooms.
That's a perfect analogy. You're hitting on something crucial there. That's precisely why monoliths really excel in scenarios needing strong data integrity. ACD transactions are just simpler.
Okay. What else defines them?
Thirdly, we have tight coupling. The components within the monolith are highly interdependent. They often make direct in-process function calls to each other.
So they talk directly, not over a network.
Exactly. This is where the monos part really kicks in. They're not separated by network calls. This direct communication, happening in the same memory space, is a fundamental driver of their performance advantages. No network latency between internal parts.
Makes sense. Faster calls.
Much faster.
Yeah.
Fourthly, there's usually a unified technology stack. The entire application typically uses consistent programming languages, frameworks, tools, you name it, across all its layers.
So everyone's speaking the same language, metaphorically.
Right. This significantly reduces the cognitive load for developers. They're not constantly switching contexts, learning new languages, grappling with different tech stacks for various parts of the system. It really fosters deeper expertise within a single set of technologies.
That consistency sounds like a breath of fresh air for developers, not having to be, a polyglot programmer just to understand one system.
It absolutely streamlines things like onboarding and day-to-day development. And finally, there's centralized business logic. All the core business rules, the processes, the decision-making logic, it's all contained within this single application boundary.
One place for all the important stuff.
Yeah. It establishes a clear, single source of truth for your application's core functionality. This can simplify auditing, ensure rules are applied consistently everywhere. It's all right there.
That makes a lot of sense. It sounds like a very almost intuitive way to build software, especially thinking back in the early days of computing. But then, like you said, it fell out of favor, only to reemerge now. How did it become so dominant historically, and what led to that initial decline before this surprising resurgence?
You're spot on. It was indeed the foundational approach for enterprise applications for decades. It really dominated the landscape from, say, the 1960s right through the early 2000s.
Wow, that's a long run.
A very long run. And its emergence was a direct response to the practical constraints of early computing. I mean, think about that era. Computing resources were incredibly limited. Memory was expensive. CPU cycles were precious.
Right, hardware wasn't what it is today.
Not even close. And deployment mechanisms were primitive, often manual steps, maybe simple shell scripts to get software running. And maybe most critically, distributed computing. It was prohibitively complex back then, incredibly expensive, notoriously unreliable.
Like a recipe for disaster.
Pretty much. Trying to coordinate multiple independent services across shaky networks was a nightmare. So building a single, coherent, self-contained unit was simply the most practical, the most manageable way to handle software complexity at the time.
So you could say necessity was the mother of monolithic invention. It was just the only sane way to build anything significant back then.
Absolutely. And its history isn't static. It didn't just appear and vanish. It's more of a dynamic journey, you could say, marked by 3 distinct phases. In the early computing era, think 1960s to 1990s, mainframe applications were inherently monolithic. They had to be really constrained by the centralized processing models and the hardware limitations of the time. These were the big iron behemoths managing huge amounts of data for large organizations.
Right, the classic mainframes.
Then came the client-server period, roughly the 1990s and early 2000s. Here, desktop applications and early web systems still largely maintained monolithic server architectures. Even as we saw client-side separation starting to emerge, the server often remained a single, powerful entity doing most of the work.
Okay, so the server was still the monolith.
Largely, yes. And what's fascinating is that in the modern web era, from the 2000s to today, even with the rapid rise of SOA and then microservices, monolithic patterns didn't just disappear, they adapted.
How so?
They started evolving to incorporate modular design principles internally. They even embraced modern cloud-native deployment strategies like containerization. So it wasn't just an old concept gathering dust. It matured, became more sophisticated internally, almost preparing it for this comeback.
And now, as you put it, it's the comeback kid. You mentioned that nuanced relationship with microservices, because it really seemed like everyone was heading towards microservices as the inevitable future.
That's right. Microservices definitely captured significant mind share, fueled by cloud adoption, the promise of independent teams, rapid scaling. It was very appealing.
And the market reflects that, right? You mentioned some big numbers.
It does. The microservices market itself is valued at a hefty $4.2 billion in 2024, and it's projected to surge to $13.1 billion by 2033. That's a robust compound annual growth rate of 12.7%. So it's clearly still very relevant and growing.
Okay, so microservices aren't going away.
Not at all. However, What practical real-world experience has revealed are the significant operational complexities and the often underestimated cost implications of running these distributed systems.
Ah, the hidden costs.
Exactly. And this is where the monolith's continued relevance really shines. It's often a pragmatic response to the unforeseen challenges and complexities that distributed architectures can bring.
So the pendulum isn't necessarily swinging all the way back, but maybe finding a more balanced middle ground, where both architectures have their rightful place.
I think that's a great way to put it. A more balanced view is emerging. And there are several compelling reasons driving this renewed interest, this reevaluation of monoliths, even in what many might still call a microservices-first world.
Okay, what are those key drivers?
Firstly, operational simplicity. For many organizations, especially those without a massive dedicated DevOps army, a single deployment pipeline just dramatically reduces complexity and infrastructure overhead.
Makes sense.
You don't have to manage, deploy, monitor, and scale dozens, maybe hundreds of independent services. This simplifies everything: CI/CD, incident response, you name it.
I can just picture the collective sigh of relief from IT teams. Fewer dashboards, fewer late-night calls trying to figure out which tiny service broke.
Absolutely. Secondly, performance optimization. This is a big one. Because all components run within the same process, there's virtually zero network latency between services.
The direct calls we talked about.
Precisely. Our research consistently shows this significantly improves response times. In fact, studies show monolithic systems can deliver up to 40% better latency performance compared to equivalent microservices.
40%? Wow.
Yeah. Imagine you're running, say, a high-frequency trading platform or an e-commerce site where every millisecond counts for conversions. That 40% isn't just a number, it's a direct hit to your bottom line, your competitive edge.
Wow, 40% better latency. That's not just a small tweak. That's a potential game changer for many performance-sensitive applications.
It's a profound difference, yeah. Thirdly, cost effectiveness. This operational simplicity and performance efficiency translate directly into lower infrastructure costs.
How much lower are we talking?
We're seeing figures showing anywhere from 50% to even 100% lower infrastructure costs compared to equivalent microservices setups.
50 to 100%, that's huge.
It is. Less complexity means fewer servers, less intricate networking, simpler monitoring tools, which are often less expensive. That's real money saved on your cloud bill every month.
Okay, that's compelling.
And finally, team productivity. Especially for smaller to medium-sized teams, a monolith often leads to faster feature delivery. You get simplified debugging, unified testing environments, a more straightforward development process overall.
Less time fighting the infrastructure.
Exactly. Less coordination overhead. The whole system is easier to reason about. Developers spend more time actually coding features and less time wrestling with distributed system puzzles.
This sounds almost too good to be true, especially given the narrative we've heard for so long. So who are the big players actually, putting their money where their mouth is, making these moves? You mentioned Amazon Prime Video. That's a huge name. Migrating back. That's where it gets really interesting. What exactly makes these monoliths work so well for giants like them? And who else is doing this?
You're right to be intrigued by the Amazon case. It's fascinating. Specifically, it was for their video quality analysis and monitoring service. They achieved a stunning 90% cost reduction by migrating back from a distributed microservices architecture built on serverless functions and step functions to a more monolithic, highly optimized system running on a single EC2 instance and ECS tasks.
90% cost cut. How?
They found the coordination overhead between their distributed components, especially the state management with step functions, was driving up costs significantly. By consolidating the logic into a single process, they eliminated all that inter-service communication overhead, drastically reduced the infrastructure complexity, simplified debugging. It was a pragmatic, business-driven choice.
So it wasn't about ideology, just pure pragmatism.
Exactly. The key takeaway there, even for an innovator like Amazon, is that architectural decisions must prioritize tangible business outcomes and practical realities over just chasing the latest technical trend or perceived best practice.
That's a massive lesson right there. It wasn't about being cool or modern. It was about what made solid business sense for that specific problem.
Precisely. And Amazon isn't alone. Consider Stack Overflow. It's a high-performance monolith serving millions of developers globally every single day.
Yeah, we all use it.
Right. And it consistently handles over 5,000 requests per second with response times typically under 50 milliseconds. Their success is built on a unified data model, super optimized caching strategies, and a deep understanding of their single code base. It just works incredibly well.
Impressive scale for a monolith.
Definitely. Then there's Basecamp. They run a hugely successful SaaS platform known for deliberately emphasizing developer productivity and operational simplicity. Built entirely on a monolithic Ruby on Rails architecture, they really demonstrate how sustainable growth and profitability can be achieved without necessarily jumping into distributed systems complexity.
Keeping it simple and effective.
Yeah. GitLab is another interesting one. They use what they call a modular monolithic architecture. So they get the organizational benefits of modular design within the monolith, but the operational advantages of a unified deployment. It allows them to develop features rapidly.
Sort of the best of both worlds, maybe.
In a way, yeah. And finally, Shopify, as we touched on earlier. Their massive monolithic core handles billions of dollars in transaction volume. It supports over 1 million merchants worldwide. Their success absolutely proves that monoliths, when designed and optimized correctly, can achieve massive enterprise scale and handle immense traffic.
Those are some seriously impressive real-world examples. They really challenge the long-held narrative, don't they? Makes you reconsider everything. Okay, let's dig deeper into how a monolith actually achieves these performance gains and operational efficiencies. What are the fundamental technical principles at play? Under the hood, what's going on?
Right. It's not just about being big or simple. It's about the inherent internal mechanics that leverage that single process model. These aren't just like minor technical details. They're the foundational elements giving monoliths their unique edge.
Okay, lay them out for us.
The first, and maybe most important, is the unified execution context. All the application components, every piece of code, runs within a single process boundary, often in the same memory space.
All together.
Exactly. This eliminates the complexity, the overhead, and crucially, the latency of inter-process communication and network protocols that you inherently get with microservices.
So no network calls between internal parts.
None. What that means in practice is direct method calls between components. Shared memory access becomes possible, and data consistency management gets much simpler, often through traditional IC transactions within a single database. Contrast that with microservices, where every interaction potentially goes over a network, introducing serialization, deserialization costs, network latency, and the need for complex things like distributed tracing just to see what's happening.
So it's like the difference between having a conversation with someone sitting right next to you versus sending an email and waiting for a reply from someone across the continent. The efficiency is just built into the proximity.
That's a perfect analogy. Really hits the nail on the head. Secondly, there's single responsibility at the application level. Now, individual modules within a modern monolith should be designed with specific responsibilities, but the entire application acts as the primary unit for deployment, for scaling, for operational management.
The whole app is the unit you manage.
Right. This dramatically simplifies monitoring, logging, troubleshooting. You look at one log stream, one set of metrics for the whole application, not this distributed mesh of potentially hundreds of different services, each needing its own dashboard, its own alerts. This unified view significantly cuts down the operational burden.
That's a massive win for reliability and developer sanity, especially when you're trying to figure out what went wrong in production at 3 a.m. No more where did that request even go mysteries.
Indeed. Huge win. Thirdly, shared state management. Monolithic applications typically manage their state through a centralized data store, often a robust relational database.
The shared database we mentioned.
Exactly. This enables strong consistency guarantees, meaning data is always up to date and consistent across the entire application at any given moment. It eliminates the immense complexity of distributed data management, where things like eventual consistency can lead to really tricky bugs and complex reconciliation logic. Here, transactions are simpler, atomic, reliable.
Easy compliance is just easier.
Much easier. And finally, technology homogeneity. The unified nature of monolithic systems naturally promotes consistent technology choices across all the application layers.
Same language, same frameworks.
Right. This consistency reduces the cognitive overhead for developers, simplifies operations, standardizes security practices, and makes implementing cross-cutting concerns like logging or authentication much, much easier. Although the flip side is less flexibility for specialized tools, but the consistency is often a major win.
So it's definitely not just a big, messy ball of mud, or at least it doesn't have to be. Modern monoliths sound like they're designed with clear internal structure, almost like microservices living inside a single deployable package, but without all that distributed communication overhead.
That's a really good way to think about it, actually.
So how do these modern monoliths actually get built? What are their typical internal components, and what are the best practices for structuring them to ensure they don't become that dreaded mud ball?
Yeah, that ball of mud stereotype really is often outdated. It's usually a relic of poorly designed older systems, not an inherent trait of the architecture itself. Modern monolithic architectures deliberately use layered design patterns to promote a strong separation of concerns while still keeping that crucial deployment unity.
So layers within the monolith.
Typically, yes. A well-structured monolith usually includes several distinct layers. At the top, you've got the presentation layer. This handles the user interface, deals with incoming HTTP requests, and is often responsible for things like authentication, authorization, managing user session state. It's what the user or other systems directly interact with.
Okay, the front door. And below that, presumably, is where the real work happens, the core intelligence.
Exactly. Below the presentation layer comes the business logic layer. This is arguably the most critical part. It contains the core application functionality, the intricate business rules, the domain logic. This is where the application's unique value proposition really lives. It coordinates actions, processes data, orchestrates the application's responses. It's like the brain, coordinating between the UI and the data.
Got it. Brains of the operation.
Then beneath that, you typically find the data access layer. This layer manages all interactions with the database. It handles things like data mapping, like ORMs, persistence operations, and effectively abstracts away the database-specific details. It provides a clean, consistent interface for the business logic layer to talk to the database without needing to know the gritty details.
So the business logic doesn't need to know if it's talking to Postgres or MySQL, ideally.
Ideally, yes. That's the goal of the abstraction. And finally, often running alongside or underneath these layers, you have an infrastructure layer. This handles cross-cutting concerns, things that are needed everywhere, like logging, monitoring, security utilities, error handling, maybe integrations with external services. It provides shared utilities for all the other layers.
So it's definitely a modular structure within the single monolith. That's clever. It gives you those immediate benefits of a monolith simplicity performance, but with an eye towards future flexibility. If, extreme scaling or totally different tech stacks become absolutely necessary for just one piece down the line.
Exactly. It prepares you for potential future evolution without paying the complexity price up front.
How are developers achieving this internal modularity? What kinds of implementation approaches and tools are they using to build these well-structured monoliths?
To get that successful internal modularity, several proven architectural approaches and design patterns are key. Domain-driven design, BDD, is huge here.
DVD, right? Heard a lot about that.
Yeah, it's about organizing the monolithic code around distinct business domains, rather than just technical layers. This creates clear, bounded contexts within the monolith. It improves maintainability, reduces the ripple effects of changes, and makes it easier for teams to focus on specific business areas without constantly tripping over each other's code.
So breaking it down by business function internally.
Exactly. Also, event-driven patterns are becoming increasingly common, even inside the monolith.
Events inside the monolith. How does that work?
By implementing asynchronous communication internally, maybe using an in-process event bus or a lightweight internal message queue, you can reduce direct synchronous coupling between different modules. This improves responsiveness and resilience without introducing the network overhead you'd get with external microservices talking over the network.
Ah, okay. Like sending internal messages around rather than making direct, potentially blocking calls between modules. That sounds like a powerful way to keep things loosely coupled, even if they're technically in the same deployment package.
Precisely. It adds flexibility. We also see API-first development being applied internally.
APIs for internal modules.
Yeah, designing the interfaces between internal modules as if they were external APIs. With clear contracts, versioning, etc., this rigorous approach really helps future architectural evolution. It makes it much easier to potentially extract a module into its own microservice later if the need arises. And it significantly improves testability because teams can work independently on different modules against those stable internal APIs.
So you're designing for potential separation later, even if you don't do it now.
Exactly. Foresight. And overarching principles like clean architecture are vital, emphasizing things like dependency inversion, strong separation of concerns. This ensures that your core business logic remains independent of the underlying technical details like the database or the UI framework. This massively improves testability and long-term flexibility.
So it really boils down to good, disciplined software engineering, right?
Yeah.
Regardless of whether it's monolith or microservices, these principles help.
Absolutely. These aren't monolith-specific ideas. They're just good software design, applied effectively within the monolithic context.
And what tools are making this whole process possible? from coding to deployment and keeping an eye on it in production.
The ecosystem around monolithic development is incredibly mature and robust. There's a wealth of powerful tools. For core development frameworks, you have giants like Spring Boot for Java. It really shines in monoliths by providing auto-configuration, sensible defaults, and a vast ecosystem that makes setting up and evolving a single unified application incredibly fast and maintainable.
Spring Boot is everywhere.
It really is. Then there's Django for Python, Ruby on Rails, .NET Core from Microsoft, and Express.js for Node.js. All of these provide comprehensive integrated platforms designed for rapid development of web applications, often monolithic ones.
Okay, standard web frameworks. What about databases? Still mostly relational.
Primarily, yes. Relational databases like PostgreSQL, MySQL, and SQL Server remain the go-to choice. Their strong consistency guarantees, ACD compliance, and mature tooling are perfect fits for the unified data model of a monolith. Though you might see some modern monoliths using polyglot persistence internally, maybe using a NoSQL database for a specific feature, but the core is often relational.
And for getting it all built, tested, and actually shipped reliably.
For building and packaging, tools like Maven and Gradle for the Java world or npmarn for Node are standard. Docker is used extensively now for containerization.
Dockerizing the monoliths.
Absolutely. You package the entire monolith into a container. This gives you consistent deployment across different environments, dev, staging, production, ensures that it works on my machine, actually translates to production reliably.
Takes away the environment headaches.
Big time. And robust CI/CD pipelines are critical. Using tools like Jenkins, GitHub Actions, GitLab CI, Circle CI, these automate the testing and deployment process, allowing for frequent, reliable releases, even with a single large code base.
Automation is key.
Non-negotiable, really. For monitoring and observability, APM tools, application performance management like New Relic, Datadog, Dynatrace are heavily leveraged. And what's particularly advantageous here is that these tools often work better or simpler with a monolith.
How so?
Because of the unified execution context. They can provide incredibly detailed end-to-end transaction tracing and performance analysis within the single process, without the complexities of distributed tracing you need to stitch together calls across dozens of microservices. It's often much simpler to pinpoint bottlenecks in a monolith using these tools.
Ah, interesting. Easier to see the whole picture.
Exactly. And finally, for optimizing performance, caching solutions are critical. Redis and Memcached are popular external caches, but monoliths can also effectively use various application-level caching frameworks, even sophisticated in-memory caches, because state and data are more centralized. This direct memory caching is something distributed systems often can't replicate as easily or efficiently.
So a whole mature tool chain exists to support building and running effective monoliths today.
Absolutely. These are the tools and practices allowing teams to build highly effective, manageable, and performant monoliths in 2025.
You mentioned some hard numbers earlier regarding performance. Let's double-click on that again, because that 40% better latency figure really caught my ear. How exactly does that manifest, and what are the other hard numbers we should really keep in mind?
It is incredible, and yeah, it's backed by empirical studies and real-world observations like the Amazon case. For latency performance, the research consistently points towards monolithic systems achieving up to 40% better latency compared to equivalent microservices doing the same work.
40% lower response time.
Effectively, yes. And as we discussed, this significant advantage comes directly from eliminating that network communication overhead between internal components, simplifying data access paths, and streamlining the execution within that single process boundary. For users, it means faster responses, less waiting, which directly impacts everything from user satisfaction to conversion rates on a website or task completion times in an application.
Okay, latency is a big win. What about throughput? How much work can it get done?
For throughput characteristics, monolithic applications generally show approximately 6% better throughput in local deployment scenarios or under moderate load conditions.
6% more requests per second, roughly.
Roughly, yeah. Now, this advantage might diminish slightly in highly elastic cloud environments designed for extreme horizontal scaling, where microservices can scale individual hotspots more granularly. But still, the unified execution model often reduces context switching and improves overall resource utilization efficiency, allowing the system to process more requests per second with the same hardware up to a certain point.
So more work done faster. What about the resources they actually consume? Are they generally more efficient?
Generally, yes, especially for small to medium scale workloads. Resource utilization patterns tend to favor monolithic architectures. Things like shared memory access between components, reduced process overhead, you're running fewer individual OS processes compared to many microservices, and less inter-process communication overhead all contribute to more efficient memory and CPU consumption.
Less overhead per request.
Exactly. Compared to distributed alternatives, which often require multiple processes, duplicated resources or libraries loaded for each service, and potentially an extensive service mesh just for communication, monoliths can be lighter weight, especially at moderate scale. This efficiency translates directly into lower cloud compute costs. You pay for less RAM, less CPU.
Lower cloud bills. Always nice.
Always nice. And significantly for error rates and reliability, monolithic systems typically demonstrate lower error rates in practice.
Fewer errors. Why is that?
It's largely due to the simplified execution path and fewer potential points of failure. The elimination of network communication between internal components gets rid of a whole class of common distributed system problems, things like transient network errors, timeout errors, connection failures, network partitions causing split-brain scenarios, partial system failures where one service is down but others try to call it.
Right. The network is often the most fragile part.
It absolutely is. By keeping communication local within the process, you inherently reduce these failure modes. Troubleshooting is also often simpler because the entire request context is usually within one process, one set of logs. This leads to a more reliable system overall.
Those are some seriously impressive numbers. 40% better latency, lower error rates, better resource utilization. That's a game changer for many applications, especially, like you said, those that are performance sensitive or need high reliability. But who exactly benefits most from these advantages? What's the real-world impact we're seeing across different industries? Where are monoliths really holding their ground or even gaining traction?
You're right to ask about the practical impact, and the market isn't, monolithic about architecture itself. It's recognizing that different patterns fit different needs, leading to this healthy coexistence we see. While microservices are certainly growing, as that KGR shows, the continued and strategic monolithic adoption in specific market segments is undeniable.
So it's not just legacy systems sticking around.
Not at all. It's often a deliberate choice. For example, you mentioned the banking, financial services, and insurance sector, BFSI. It accounts for a large share of microservices adoption for newer, customer-facing apps. But many financial institutions explicitly maintain monolithic core banking systems.
Why is that?
For their rock-solid transactional integrity, ACID compliance is non-negotiable there. Also, simplified audit trails for regulators and meeting strict regulatory compliance requirements is often easier with a unified system boundary and data store. The cost of error is just too high to introduce unnecessary complexity in those core systems.
So it's not a one-size-fits-all, but more about specialized tools for specialized jobs, even within the same company sometimes. Are there any regional differences in how these architectures are adopted, or is it pretty much a global phenomenon?
There are definitely variations. North America, for instance, tends to lead the curve on microservices adoption, often driven by aggressive cloud-native initiatives, modernizing legacy systems, maybe the influence of the big tech companies headquartered there.
Okay, U.S. leads microservices push.
Often, yeah. However, European and Asia-Pacific markets frequently demonstrate more balanced approaches. We see many organizations there adopting pragmatic hybrid strategies, maybe combining a robust monolithic core for the stable parts of the business with selective microservices for specific, highly isolated functions that need independent scaling or rapid iteration.
A more blended approach.
Exactly. A bit more cautious, perhaps, or maybe just pragmatic based on their team sizes and operational maturity. It's also really worth noting that the major cloud platforms, AWS, Azure, GCP, they all fully support both patterns. They're continuously optimizing their services to cater to diverse needs, from massive distributed systems to highly efficient monolithic deployments on containers or VMs.
So the cloud vendors aren't pushing only microservices.
Not exclusively, no. They acknowledge the need for both. There are services for container orchestration, databases, monitoring. They work well for well-architected monoliths, too. This shows strong, evolving vendor support, recognizing monoliths are a key part of the landscape.
So where are monoliths truly shining today? What are the key use cases and applications where they are still proving to be the optimal choice, even with all the microservices hype?
Monolithic architecture really demonstrates particular strengths in several critical domains, where that consistency, performance, and operational simplicity are paramount. Take e-commerce platforms, for instance.
Like Shopify?
Exactly like Shopify. Systems for content management, product catalogs, order processing, payment integration, these often benefit immensely from a monolithic implementation. The unified transaction model inherently simplifies complex things like inventory management across channels or processing multi-item orders with payments. High performance is also critical for conversion.
Makes sense, keeping the core commerce engine tight.
Right. Then there are financial services applications, core banking systems, intricate trading platforms, complex risk management applications. These frequently employ monoliths, as we discussed. The inherent ACD transaction guarantees, the simplified audit trails, the ease of ensuring data consistency across multiple related modules. These are critical for regulatory compliance and just reducing operational risk in a super sensitive environment.
That makes perfect sense for finance. Consistency is king there. And even tiny errors are incredibly costly. No room for eventual consistency drift.
Exactly. Also, content management systems, CMS, think modern publishing platforms, document management, digital asset management tools. They often leverage monoliths for their unified content model, making complex queries and relationships easier to manage. Robust search capabilities and the ability to deliver new content-related features rapidly are also benefits.
Okay, CMS platforms, what else?
Enterprise resource planning, ERP systems, are another classic fit. These big systems integrate many parts of a business, finance, HR, supply chain, manufacturing.
Like the SAPs and Oracles of the world, traditionally.
Yeah, traditionally, yes, though modern ERPs exist too. They benefit greatly from monolithic deployment to ensure seamless data consistency across all those disparate modules. Imagine trying to get an accurate real-time report across finance and inventory if they were separate microservices with eventually consistent data. A nightmare. The monolith simplifies that integrated reporting and analytics massively.
Yeah, consistency across business functions is key for ERP.
Absolutely. And finally, for real-time applications, think online gaming platforms, high-frequency trading systems, industrial control, or monitoring applications. Here, the low-latency characteristics of monoliths are often essential. That elimination of network communication overhead we keep talking about is absolutely critical for achieving the sub-millisecond response requirements and maintaining a competitive edge. You just can't afford network jitter in those scenarios.
It's fascinating to see how broadly applicable and frankly critical monoliths still are, especially in these core sectors where consistency, performance, reliability, rapid feature delivery are paramount.
Let's revisit some of those success stories you mentioned, Amazon, Stack Overflow, Shopify, and really try to learn from these giants. What are the key takeaways from their experiences that we can maybe apply to our own decisions?
Right. Looking at the giants gives us concrete lessons. The Amazon Prime Video case study remains perhaps the most striking, maybe the most counterintuitive one. That 90% cost reduction by migrating back from microservices to a monolith for that specific video analysis service.
Still mind-blowing. It is. Their initial microservices architecture, using step functions and Lambda, had introduced significant operational overhead and spiraling costs, primarily due to the sheer number of state transitions and inter-service calls for each video processed. By consolidating that logic, they dramatically simplified the infrastructure, reduced latency, and slashed debugging time. The key takeaway is profoundly simple, but often ignored. Architectural decisions should always prioritize tangible business outcomes and pragmatic realities over just following technical trends or perceived industry best practices. It's about solving your specific problem effectively, not adopting someone else's solution just because it's popular.
It's a huge lesson right there. It wasn't about being trendy or cloud native maximalist. It was about what made actual quantifiable business sense for that workload.
Precisely. Then there's Stack Overflow, an enduring example of a high-performance monolith that just keeps delivering. It consistently serves millions of developers, handling, as we said, over 5,000 requests per second with response times under 50 milliseconds.
And they're pretty open about their architecture, right?
They are, which is great. Their success isn't just luck. It's built on deliberate choices. A unified data model, highly optimized caching strategies implemented directly within the monolith, they do a lot of in-memory caching, and a deep, holistic understanding of their single code base that allows for system-wide performance tuning. They really own their stack.
So deep expertise in a simpler stack pays off.
It certainly can. Basecamp is another great example. They run a hugely successful, sustainable SaaS business. Their explicit commitment to a monolithic Ruby on Rails architecture has allowed them to maintain high developer productivity, focus on operational simplicity, and keep their team relatively small and focused. They prove that significant growth and profitability can absolutely happen without the inherent complexities and costs of distributed systems.
The keep it simple, stupid principle applied effectively.
You could say that. GitLab employs that modular monolithic architecture we discussed. They combine the organizational benefits of clear internal module boundaries with the operational advantages of a unified deployment. This allows them to iterate incredibly rapidly and deliver a vast number of new features continuously to their huge user base, even with a large code base.
So modularity within the monolith is key for them.
Crucial for their velocity, yes. And finally, Shopify. We keep coming back to them because the scale is just so impressive. Their monolithic core handles billions in transaction volume, supports over 1 million merchants. Their ability to achieve the scale on a monolith is a testament to really disciplined engineering, rigorous automated testing, continuous performance optimization, and likely a very well-structured modular design internally. It demonstrates that monoliths, when properly engineered and managed, are not inherently limited in scale for many, many types of applications.
These really aren't small players or niche cases. They prove that monoliths can absolutely scale to enterprise levels, handle immense traffic, and support huge businesses when designed and optimized correctly. So beyond the impressive performance numbers and these compelling success stories, what's the tangible business value here? What kind of return on investment or ROI are we talking about for organizations choosing this path?
Yeah, let's talk brass tacks. The quantitative analysis, looking across studies and case reports, really reveals significant ROI across several key areas. First, development cost analysis. Monolithic architectures consistently show 30% to 50% lower development costs, especially for small to medium-sized teams.
30 to 50% cheaper to build.
Sure. It's a direct result of reduced coordination, overhead, fewer meetings, less complex planning. Simplified testing procedures, you don't need elaborate distributed integration test setups. And unified tooling requirements, everyone uses the same stack. Plus, the learning curve for new developers joining a monolithic code base is often significantly shallower than needing to understand a complex web of microservices. They can become productive faster.
Those cost savings are massive, especially for startups or companies with tighter budgets trying to maximize their runway. That's real money back into innovation or marketing or just surviving longer.
Absolutely. It can be the difference between launching or not, and when it comes to actually getting features out the door, there are significant time-to-market advantages. Monoliths often enable 25% to 40% faster feature delivery, particularly for established applications or when adding features to an existing system.
Faster time to market, how does that work?
Again, it comes back to simplicity. Simplified deployment pipelines push one thing. Unified testing procedures run one comprehensive test suite, and reduced coordination complexity inherent in a single codebase. This advantage is especially pronounced for those smaller to medium teams working on well-defined product requirements. They can just iterate and deliver value much more quickly without getting bogged down in cross-service dependencies.
Okay, so potentially much faster iteration cycles.
Often, yes. For operational cost benefits, the savings can be even more dramatic, as we saw with Amazon. Infrastructure costs can be 50% to 100% lower compared to equivalent microservices implementations doing the same job.
50 to 100% cheaper to run. That's staggering.
It really is. It stems from reduced container orchestration overhead, fewer containers, simpler scheduling, simpler monitoring tools, one system to watch, and significantly more efficient resource utilization, as we discussed. You're simply paying for fewer active servers, less complex networking, maybe cheaper observability tooling.
So, cheaper to build, cheaper to run, and faster to deliver features. That sounds like the trifecta for any business leader.
It's a very compelling proposition when the context is right. Furthermore, for maintenance cost reduction, the long-term costs often favor monolithic architectures if the team size remains relatively stable and the requirements evolve predictably. The unified code base reduces context switching for developers doing maintenance, simplifies debugging across features, and streamlines things like security patch one system, not 50.
Easier to keep secure and up-to-date over time.
Potentially, yes. And finally, there's risk mitigation value. Monoliths, arguably, reduce certain kinds of operational risk. Their simplified failure modes mean fewer types of things can go wrong compared to complex distributed systems. Unified monitoring provides clearer insights when things do go wrong. And predictable scaling patterns often make capacity planning more straightforward. This reduced complexity can translate to a lower probability of cascading failures and generally improve system reliability, leading to less downtime and greater business continuity.
Fewer unknown unknowns, maybe.
Perhaps. And of course, let's not forget the performance ROI. That 40% latency improvement, that 6% throughput advantage, these aren't just technical stats. They translate directly to a measurable business value for performance-sensitive apps. Higher customer satisfaction, increased engagement, better conversion rates, maybe even reduced operational costs just due to more efficient resource usage under load.
So it's clear not only can monoliths perform exceptionally well, but they can also save you a significant amount of money and get features to market faster in the right circumstances. That's a truly compelling argument. But we absolutely know, there's never a single perfect solution in software architecture. It's always a balancing act. What are the main alternatives that organizations consider, and how do monoliths really stack up against them, the good, the bad, and the ugly?
You're absolutely right. It's a whole spectrum of choices, and context is everything. Each pattern has its own inherent strength and weaknesses. The primary alternative everyone talks about, of course, is microservices.
Right, the reigning champ,
Yeah.
arguably.
Arguably, yeah. Breaking applications into small, independently deployable services, each typically owning its own data, communicating via APIs. As we discussed, the market's growing at 12.7% CAGR, so it's definitely prominent.
Okay, microservices. What else is on the menu?
Then there's service-oriented architecture, SOA. This is an older distributed pattern, often characterized by larger service granularity compared to microservices, and frequently involving integration via an enterprise service bus, ESB. It's less common for new projects now, but still exists in many enterprises. We also have serverless architecture, heavily leveraging function as a service, FAS, like AWS Lambda or Azure Functions.
Function-based, paper execution.
Exactly. Event-driven, often stateless functions that auto-scale, and you abstract away server management entirely. Very different model. And the important hybrid approach we've touched upon, the modular monolith. This aims for the best of both worlds. Maintains the single monolithic deployment unit, but enforces strong internal modularity with clear internal API boundaries.
Trying to get monolith simplicity with microservice-like internal structure.
That's the goal. Each of these has its sweet spot. The absolute key is understanding when to use what, based on your specific needs and constraints.
So let's put it on the scale then. We've talked a lot about the advantages of monoliths, the performance, the cost savings, the operational simplicity. But what are their inherent limitations, the downsides, that people absolutely need to be aware of before they jump in and choose this path?
Yeah, it's crucial to have that balanced view. No architecture is a magic silver bullet. While monoliths offer those compelling advantages we've covered, like the performance superiority, that 40% latency, 6% throughput, the operational simplicity, 100% lower infra costs, the development productivity boost, 25 to 40% faster delivery for smaller teams, the inherent cost effectiveness, and that strong ACID compliance for data consistency, they absolutely come with a set of significant limitations too.
Okay, let's hear the downsides.
Probably the biggest one people point to is scaling constraints. With a monolith, you often have to scale the entire application horizontally, meaning spin up more identical copies, even if only one small component or feature is experiencing high load.
Right, scale the whole thing and nothing.
Pretty much. This can lead to significant resource waste, as you might be over-provisioning resources, CPU, RAM, for parts of the application that are sitting idle, just to handle the load on one busy part. This is precisely where microservices shine, as they allow you to scale individual services independently based on their specific needs.
That makes perfect sense. If only your image processing module is getting hammered, you still have to spin up a whole new instance of your entire application with the user profiles module, the billing module, everything else just sitting there just to handle those image requests. That feels inherently inefficient for highly variable loads.
It definitely can be for highly elastic variable loads where different parts scale very differently. Then there's technology lock-in. That unified technology stack, while great for simplifying development initially, prevents you from easily adopting the optimal, perhaps specialized technology for specific components later on.
Can't use the best tool for every single little job.
Exactly. You can't easily decide to use, say, a super fast niche graph database for just your social connection feature if the rest of your application is standardized on PostgreSQL. You're kind of stuck with the lowest common denominator across the whole application. This can limit innovation at the component level or lead to less than ideal technical solutions for certain problems.
So less flexibility in tech choices. What else?
Deployment risk. This is a big operational concern because the entire application is a single deployment unit. Any change, no matter how small or isolated, requires redeploying the entire system.
The whole thing goes out at once.
Yes. This inherently creates a higher blast radius and thus a higher risk of total system failure during updates. If the deployment fails or introduces a critical bug, the whole application can go down. While modern deployment strategies like blue-green deployments or canary releases can mitigate this risk, they are still often more complex to manage for a large monolith, and the potential impact of failure is broader than deploying a single, isolated microservice. Our research suggests monolithic deployments can potentially have 15% to 25% higher failure rates per deployment event compared to incremental microservices deployments, simply due to the larger scope of change in each release.
So one small bug in a seemingly unrelated part of the code could potentially bring down the whole application if you're not incredibly careful with testing and rollout. That's a significant operational risk to manage.
It absolutely is. Requires very mature testing and deployment practices. And then, related to what we touched on earlier about team productivity, there are potential team scaling challenges. As development teams grow very large, working concurrently on a single monolithic code base can lead to significant coordination bottlenecks. You get frequent merge conflicts, longer integration times, developers stepping on each other's toes. Conway's law really bites here. The structure of your system tends to mirror the communication structure of your organization.
Uh-huh.
A single large code base can really constrain the autonomy and parallel work capability of very large independent teams.
So it works great for small teams, but can become a bottleneck for huge organizations.
It often does, yeah. Finally, there's limited fault isolation. If one component or module within the monolith fails catastrophically, maybe due to a memory leak, a runaway thread consuming all CPU, or an unhandled exception, it can potentially cascade and affect the entire application process, bringing the whole thing down.
One bad apple spoils a whole bunch.
Potentially, yes. This reduces overall system resilience compared to well-designed distributed architectures that implement patterns like bulkheads or circuit breakers to isolate failures within individual services and prevent them from taking down the entire system.
Okay, so definitely not a perfect picture. It's never a one-size-fits-all, is it? We really do need to weigh these pros and cons very, very carefully, specific to our own context. So how do you decide, for an organization listening right now, maybe facing this choice for a new project or re-architecture, how can they objectively choose the right path for their particular needs? How do they move beyond the hype and make a smart call?
This is where moving towards a structured decision framework becomes absolutely invaluable. It helps you get past the buzzwords, past the blog posts, and focus on what genuinely fits your unique situation.
Okay, what factors should be in that framework?
First and foremost, consider team size and structure. This is huge. Monoliths are generally optimal for smaller, cohesive teams. Think under 8-10 developers, maybe up to 12-15 if they're very well coordinated. For larger teams, the coordination overhead and potential for merge conflicts can become prohibitive, making distributed patterns, like microservices or modular monoliths evolving towards services, more suitable for enabling team autonomy and parallel development streams. Your organizational structure should ideally align with your architecture to minimize friction. That's Conway's law in action.
So if you're a lean, agile startup with one or two small teams, a monolith might truly be your best friend to get off the ground quickly and efficiently.
Precisely. It optimizes for speed and simplicity in that context. Secondly, assess application complexity and scope. Applications with well-defined boundaries, stable requirements, and relatively cohesive core business logic often favor monoliths. If the core functions are tightly related and not expected to fragment wildly or require vastly different scaling characteristics, a monolith provides simplicity and speed. However, if you anticipate a highly volatile domain or an extremely complex application requiring independent evolution and scaling of many disparate parts, a distributed approach might offer more long-term flexibility despite the initial complexity cost.
So how complex and changeable is the problem space?
Exactly. Third, evaluate your performance requirements. This is critical. Latency-sensitive applications that absolutely need sub-100 millisecond response times or systems requiring very high, consistent throughput will often benefit significantly from the inherent speed and reduced communication overhead of a monolith. If performance is a primary driver, the monolith has a strong advantage.
And what about the organization's existing capabilities and their budget? Those must be enormous factors.
Absolutely critical. Fourth factor, operational maturity. Organizations with limited DevOps expertise, smaller operational teams, or less mature operational capabilities, monitoring automation, incident response, will find monoliths significantly simpler and less costly to manage day to day. Distributed systems demand substantial operational investment, specialized tooling, service mesh, distributed tracing, and deep expertise in areas that many organizations just don't have readily available. Be honest about your team's operational readiness.
Don't bite off more than you can chew operationally.
Exactly. Fifth factor, budget and resource constraints. Cost-sensitive projects, startups, or internal tools absolutely favor monoliths due to their inherently lower infrastructure and operational overhead, and often lower initial development costs. They allow you to achieve more functionality with less investment, which is vital for new ventures or projects with tight funding.
Get more bang for your buck, essentially.
Pretty much. And finally, number 6, regulatory and compliance requirements. Applications operating in highly regulated industries like finance or healthcare, which demand strong data consistency guarantees, clear and simple audit trails, and perhaps easier security validation across a single system boundary, often find monoliths highly advantageous due to their unified data store and simpler transaction management.
Makes auditing and proving compliance simpler.
Often, yes. It's just fewer moving parts to certify or audit. So using a framework like this, focusing on your team, your problem, your performance needs, your operational reality, and your budget. That's how you move past the hype. It really becomes about organizational fit over purely technical sophistication or trendiness.
Organizational fit over technical sophistication. I like that. That really changes the perspective. So summing all that up, what are the overarching trade-offs people really need to wrestle with when making this architectural choice? What's the core balancing act they're performing?
It really is a classic balancing act, one that pretty much defines software architecture choices. You're constantly trading one set of benefits for another set of challenges. First, it's simplicity versus flexibility. Monolithic architectures inherently optimize for simplicity, especially in development speed and operational management early on. Distributed architectures, conversely, optimize for flexibility, independent scaling, independent technology choices, independent deployments, but they do so at the cost of significantly increased complexity. You have to prioritize. Do you need simplicity now or flexibility later?
A classic trade-off.
Absolutely. Second, performance versus scalability. Monoliths typically provide better raw performance and lower latency for moderate predictable loads due to those direct function calls and lack of network overhead. Distributed architectures, however, generally excel at massive horizontal scalability and handling highly variable, potentially immense loads by distributing work across many independent, individually scalable services. So raw speed versus ultimate scale potential.
So monoliths are faster out of the gate and efficient for typical loads, but microservices might be better if you anticipate needing to handle truly massive, unpredictable spikes on specific parts of the system independently.
That's a good summary, yeah. Third trade-off, development speed versus operational complexity. Monoliths generally enable faster initial development and deployment, particularly for smaller teams, because there's just less inter-service coordination and infrastructure setup. Distributed architectures, while potentially enabling faster long-term feature delivery for very large, highly parallelized teams, typically require a significant upfront operational investment and introduce substantial ongoing operational complexity, monitoring, tracing, deployment coordination. Faster start versus potentially more complex scaling later.
Invest complexity upfront or potentially deal with scaling limitations later.
Right. Fourth, cost versus capabilities. Monolithic architectures generally minimize infrastructure and operational costs due to their efficiency and simplicity. Distributed architectures, while offering advanced capabilities like fine-grained scaling, independent technology stacks per service, and potentially higher resilience through fault isolation, almost always come at a higher total cost of ownership when you factor in infrastructure, tooling, and specialized personnel. You must evaluate the true total cost, not just the initial development estimate.
Lower costs versus more advanced features.
Often, yeah. And finally, team autonomy versus coordination overhead. Distributed architectures can enable greater team independence and autonomy, allowing teams to own their services end-to-end, but achieving this effectively requires sophisticated coordination mechanisms, strong API contracts, and significant cultural shifts. Monoliths inherently simplify coordination for smaller, cohesive teams, but can introduce significant coordination overhead and become bottlenecks for very large teams trying to work concurrently on the same shared code base. So it's truly a classic balancing act. There's no magic bullet, no single right answer. Only smart, informed choices based on your specific context, your priorities, and your long-term vision.
There's no magic bullet, only smart choices based on your specific context. That's a perfect summary and a crucial reminder for everyone listening. So for those who go through this process and decide that, yes, a monolith is indeed the right path for them, what are the common pitfalls they should proactively try to avoid? What kind of challenges might they still face down the road? And crucially, how do they overcome them to ensure a successful, maintainable monolithic journey?
Yeah, it's vital to be eyes wide open about the potential challenges, even after deciding a monolith is the right fit. But the really good news is that these challenges are well understood, and there are established best practices and solutions to mitigate nearly all of them.
Okay, so what's pitfall number one?
The first major one is allowing code-based complexity and maintainability to spiral out of control. As a monolithic application grows over time, especially if it gets beyond, say, 100,000 lines of code without strong internal structure, it can become increasingly difficult for new developers to understand. And even for existing teams, making changes without introducing regressions becomes harder and slower. If you don't enforce those module boundaries we talked about, you can end up with tangled dependencies that spaghetti code, which makes any change risky and development velocity grind to a halt.
So the big ball of mud stereotype, while often unfair initially, can become a self-fulfilling prophecy if you're not disciplined about internal structure and technical debt.
Precisely. Vigilance is required. And then there are the deployment bottlenecks and risk we discussed earlier. That single deployment unit means any change, no matter how small, requires redeploying the entire system. This inherently increases the potential impact radius of any failure during deployment. As mentioned, studies suggest monolithic deployments can have 15% to 25% higher failure rates per deployment event compared to smaller, incremental microservices deployments, simply because more code is changing at once. If something goes wrong during that deploy, the whole application can be affected.
So that one small bug, or even just a bad configuration change pushed with the code, could potentially bring down the entire system if you're not incredibly meticulous about your pre-deployment testing and your rollout strategy.
Mhm.
That's enough to make any operations team nervous.
It absolutely is. Robust automation and testing are paramount. Another challenge is that technology constraint, or what some call innovation debt. A unified technology stack, while simplifying things, prevents teams from easily adopting the absolute optimal, perhaps specialized technology for every single component. You might be stuck using your standard relational database for a feature that would scream for a time series database just because it has to fit the overall stack of the monolith. This can sometimes lead to suboptimal technical solutions or slower adoption of emerging technologies that could provide a competitive advantage.
You might miss out on the perfect tool for a specific job sometimes.
You might. For large teams, those team collaboration issues and merge conflicts can become a major headache. Research and experience indicate that teams exceeding that 10-12 developer mark working on a single code base start experiencing exponentially increasing coordination costs. More time spent resolving merge conflicts and version control, longer and more complex integration testing cycles. It just slows everyone down.
The communication overhead explodes.
It really can. And finally, that limited fault isolation issue. If one component within the monolith fails badly, runs out of memory, gets stuck in an infinite loop, throws uncut exceptions that can potentially destabilize or crash the entire application process. This reduces overall system resilience compared to well-designed distributed architectures that have mechanisms like bulkheads or circuit breakers to contain the blast radius of a single service failure.
So these are real challenges, and they're not just purely technical issues either, are they? They seem deeply tied to how people work together and how organizations are structured. What about the organizational challenges beyond just team size that might trip up a monolithic project?
You're absolutely right. The organizational aspects are just as critical, if not more so. Conway's law looms large here. Monolithic architectures inherently thrive with small, cohesive teams that can communicate and coordinate effectively, often informally. When an organization grows rapidly or needs to scale development across many teams, it often needs to consciously evolve its architectural approach, maybe towards modular monolith or services, or very carefully structure its teams and communication pathways to avoid creating friction with the single monolithic codebase. You can't just throw more people at a monolith indefinitely without restructuring something.
The org chart needs to match the architecture, or vice versa.
Ideally, yes. Then there's change management and release coordination. Successfully coordinating releases across multiple development teams, all contributing to a single codebase, requires a highly sophisticated process. You need strong practices like feature flags to decouple deployment from release, careful branch management strategies like Git flow, and incredibly robust automated integration testing to ensure changes from different teams don't break each other. It demands discipline.
More process needed as the team grows.
Definitely. Knowledge management also becomes crucial as the code base gets large. Big monoliths demand comprehensive documentation, architectural overviews, clear module interface specs, operational runbooks, and effective onboarding processes are vital to reduce the potentially steep learning curve for new team members trying to understand a large, complex system. You need to invest in keeping that knowledge accessible. And finally, those innovation constraints we touched on. The unified deployment model can make certain types of experimentation, like A/B testing new features on just a small subset of users, more complex compared to microservices where you can route traffic to different versions easily. You might need more sophisticated feature flagging or traffic routing infrastructure to achieve the same level of experimentation, which could potentially slow down innovation velocity for certain product development approaches.
Okay, so a lot to watch out for, both technically and organizationally. But you said there are solutions. How do we mitigate these risks? What are the tried and true best practices for proactively building a robust and successful monolith? One that not only avoids these pitfalls, but actually thrives and remains maintainable long term.
This is where disciplined design, proactive planning, and just solid engineering rigor really make the difference. The single most crucial practice, bar none, is embracing modular design within the monolith.
That modular monolith idea again.
Exactly. This is non-negotiable for any non-trivial monolith today. You must implement clear internal module boundaries, use intelligent package structures, enforce strict interface segregation between modules so they only talk through well-defined APIs, even internally, use dependency injection patterns heavily to manage coupling, and leveraging those domain-driven design principles we talked about helps establish logical boundaries that map to the business, which also makes future extraction into microservices much easier if that ever becomes truly necessary. Modularity is key.
So build internal walls, even if it's one big house.
Perfect analogy. Second, automated testing. Comprehensive test suites are absolutely vital. Unit tests for individual components, integration tests for interactions between modules within the monolith, and end-to-end tests that simulate user journeys. A high degree of test automation provides rapid feedback, prevents regressions, and builds the confidence needed to make changes and deploy frequently, even with a large code base. Test-driven development, TDD, and robust continuous integration CI pipelines are your best friends here.
So a strong, fast-running, automated test suite becomes an absolute must-have safety net. No shortcuts allowed on testing.
Absolutely none. Third, performance optimization needs to be continuous. Don't wait for it to become slow.
Yeah.
Actively leverage application performance management, APM tools from day one. Conduct regular database query analysis and optimization. Implement multi-level caching strategies, in-memory, distributed cache like Redis. Perform regular code profiling to find hotspots.
Monoliths can be incredibly performant, often more so than microservices, but it requires ongoing attention and optimization effort.
Proactive performance tuning, not reactive. Exactly. Fourth, code quality and technical debt management. You have to actively fight entropy. Regular code refactoring to improve structure, thorough code reviews involving multiple team members, and using automated static analysis tools, linters, code quality checkers, are essential to prevent the code base from degrading into that ball of mud over time. Make paying down technical debt a regular part of your development cycle.
Treat code quality as a feature.
You have to. Fifth, documentation and knowledge management. Don't let it be an afterthought. Maintain comprehensive architectural overviews, keep clear API specifications for internal module interfaces up to date, document operational procedures and runbooks. Good documentation is essential for effective team collaboration, reducing the bus factor, what happens if a key person leaves, and enabling efficient onboarding of new developers onto a potentially large system.
Write it down.
Please. Sixth, DevOps and automation. Embrace automation everywhere possible. Fully automated CI/CD pipelines for testing and deployment. Infrastructure as code, IAC, practices using tools like Terraform or CloudFormation to manage your environments consistently. And robust monitoring and alerting systems are critical for efficient operations and rapid response to production issues. Automation reduces manual errors and operational toil. Seventh, bake in security best practices from the start. Implement defense in-depth strategies. Practice rigorous input validation everywhere. Use robust authentication and authorization mechanisms consistently across the application. Don't treat security as something you bolt on at the end.
Security by design.
Exactly. And finally, number 8, capacity planning and scalability. Even though scaling a monolith is simpler in some ways, you still need to plan for growth. Continuously monitor resource utilization and performance under load. Utilize horizontal scaling effectively using load balancers, auto-scaling groups for your containerized monolith instances. And critically, focus on optimizing and potentially scaling your database, as the centralized database is often the primary bottleneck for a monolith at high scale. These practices, applied consistently, truly transform a potential monolith monster into a highly effective, manageable, reliable, and performance system that can serve a business well for a very long time.
That's a fantastic checklist of best practices. It makes it clear that building a successful monolith isn't about avoiding complexity altogether, but about managing it intelligently through discipline and good engineering. So looking ahead now, it's clear the architectural landscape isn't static. It's constantly adapting, integrating lessons learned, maybe finding a more nuanced balance. What's the future outlook for monolithic architecture in this continually evolving landscape? What trends should we be watching closely in 2025 and beyond?
Yeah, we're seeing some truly fascinating and I think quite pragmatic trends emerge right now. There's a definite sense of a post-microservices movement maturing. Not an outright rejection, but a move beyond the blanket assumption that distributed architectures are always inherently superior. Organizations are increasingly recognizing that for many contexts, the complexity introduced by microservices often exceeds their actual organizational capabilities or operational maturity. This can lead to performance degradation, immense operational overhead, and ironically, reduced overall productivity compared to a well-structured monolith.
So people are getting smarter, more discerning about when and where to actually use microservices rather than just defaulting to them everywhere. That sounds like a healthy sign of maturity in the industry.
Precisely. It's a move towards more thoughtful trade-offs. And this shift is directly fueling a significant modular monolith renaissance. These architectures, single deployment but strong internal modularity, are experiencing substantial adoption growth. Industry surveys are indicating that as many as 60% of new enterprise applications are now actively considering modular, monolithic approaches as a primary architectural option, sometimes even the default starting point. They really aim to strike that appealing balance. The operational simplicity of a single deployment unit combined with the internal modularity needed for long-term maintainability and future flexibility.
60% considering modular monoliths. That's huge.
It's a major shift in thinking. We're also seeing the continued rise of sophisticated hybrid architecture patterns. Organizations intelligently combining robust monolithic cores for the stable, well-understood parts of their business with selective microservices for specific functions that truly benefit from independent deployment, specialized technology, or extreme independent scaling. Maybe the user notification system or a machine learning inference engine gets broken out, while the core transaction engine remains monolithic.
That sounds like a really pragmatic middle ground. Take advantage of the strengths of both approaches where they make sense.
It absolutely is. Pragmatism is the key word. Furthermore, AI-enhanced development tools are poised to significantly improve monolithic development productivity in the near future. We're starting to see tools emerge that offer automated code analysis to identify coupling issues, provide intelligent refactoring assistance to improve modularity, and even offer architectural guidance specifically for maintaining and evolving large monolithic code bases. AI could become a powerful ally in managing monolith complexity.
AI helping us keep our monoliths clean.
Yeah.
Interesting.
Potentially, yeah. For industry predictions looking ahead, monolithic architectures are widely expected to maintain a substantial market share. Estimates suggest they'll account for 40% to 60% of new enterprise application development through 2030. Their strength will likely remain particularly pronounced in small to medium enterprises, SMEs, and for cost-sensitive projects where operational simplicity and efficiency are paramount.
So that's a significant forecast. It indicates real staying power and a firm rejection of the outdated idea that monoliths are somehow obsolete or just for legacy systems.
Absolutely. They're a valid modern choice. We're also witnessing continued cloud-native monolith adoption. The major cloud platforms are increasingly optimizing their services for monolithic deployment patterns, not just microservices. They're offering improved container orchestration features tailored for single large applications, better auto-scaling capabilities for stateful monoliths, and more sophisticated observability tools that work well with unified application contexts. This shows the major cloud providers are actively investing in supporting well-architected monoliths as a viable and efficient architectural choice on their platforms.
So the cloud itself is adapting to support monoliths better.
Definitely. And finally, in specific, highly regulated sectors, think financial services, again, healthcare, government compliance drivers, mean they will likely continue favoring monolithic architectures for their core systems. The inherent audit simplicity, the robust data consistency guarantees, and the potentially reduced attack surface complexity compared to a sprawling distributed system often make monoliths the lower risk choice when regulatory scrutiny is high.
This has been an incredibly insightful deep dive, really peeling back the layers on an architectural choice that, frankly, many people, including myself, sometimes might have thought was mostly relegated to the past. So, as we wrap up, what are the absolute key takeaways, the core messages we should leave our listeners with today?
Okay, let's boil it down to the essentials. First, performance and cost are real advantages. Monoliths can offer compelling, empirically backed benefits, including up to 40% better latency performance and potentially 50% to 100% lower infrastructure costs in suitable contexts. These aren't just theoretical, they're tangible, measurable benefits that directly impact your bottom line and your user experience. Don't dismiss them.
Performance and cost. Got it.
Second, organizational alignment is crucial. Success with any architecture, but perhaps especially monoliths, is profoundly driven by team size, structure, and communication pathways. Monoliths are often optimal for smaller, cohesive teams, typically under 8-10 developers, strongly aligning with Conway's Law. Amazon Prime Video's dramatic 90% cost reduction by migrating back stands as a powerful, real-world testament to how aligning your architecture with your true business outcomes and your actual organizational capabilities is paramount. It's not just about the tech trends.
Match the architecture to the team and the goal. Makes sense. And crucially, the idea that monoliths aren't necessarily just one big, unmanageable blob anymore.
Exactly. That's takeaway number 3. Modular patterns are the modern standard. Modern monoliths, built with disciplined internal modularity using clean architectural principles like DDD and clear interfaces, provide crucial flexibility for future evolution. You can achieve the simplicity and speed benefits of a monolith now, while retaining the option to more easily extract specific services later, only if and when the need truly justifies the complexity. It offers a path, the best of both worlds potentially.
Modularity gives you options.
It absolutely does. And finally, takeaway number 4, maturity and relevance persist. The continued advancements in cloud platforms, the robustness of modern development frameworks like Spring Boot, Rails, .NET Core, and the sophistication of monitoring and deployment tools ensure that monolithic approaches remain highly relevant, continuously enhanced, and are far, far from obsolete in the modern software landscape. They are a viable, powerful tool in the toolbox.
So putting this all together, what does this mean for you, our listener, as you stand at that architectural crossroads, trying to make the best decision for your next project or system?
Ultimately, the best architecture. It really isn't about blindly following the latest industry trend or adopting the most technically complex solution just for its perceived sophistication or because it looks good on a resume. It's about making evidence-based, pragmatic decisions, decisions that truly align with your specific team's capabilities, your real budget constraints, your operational maturity, and your overarching business goals. At the end of the day, it's about organizational fit over technical fanfare.
So the next time you're thinking about building a new system, or perhaps re-architecting an old one, before you automatically jump on the microservices bandwagon just because everyone else seems to be, maybe pause. Ask yourself, could the perceived simplicity and constraint of a monolith actually be its inherent strength for my specific project, my team, right now? What does your organization truly need today versus what the loudest voices or the coolest tech blogs are proclaiming? Challenge those long-held assumptions, diving deep into your own specific context with a critical, pragmatic eye, and you might just find that the old, perhaps underestimated monolith is exactly the new solution, maybe even the competitive edge you've been looking for all along.